Okay, so let's look at the three basic stages of amplification and see the noise behavior in them. So the first stage, we can do it in MOSFET, for example, right? So if you think about a MOSFET, let's look at a very basic common emitter stage. And let's think about the noise sources that you have. So you have a load resistance R1. You have this, the transistor with a certain W over L. And what are the noise sources we should take into account? For now, let's just assume that we have two sets of, so we use the thermal noise of the resistor, right? So you get 4 kT over R1. We have the channel noise of the MOSFET, which is 4 kT gamma GD0. And then we also have, let's say, the flicker noise of the MOSFET, the 1 over F noise, which we model in this case as a voltage source at the input, which would be 4 kT, no, sorry, not 4 kT, KF over Cox WLF. So you have these three noise sources, let's say, and you're trying to determine what is the total input referred noise, for example. Now, if you're looking purely at low frequency stuff, the input impedance is, for MOSFET, is a special case because the input impedance is infinity at low frequencies, which basically means that a voltage source is sufficient. An input referred voltage source is sufficient. If you're looking in general at some Z pi, it can be at CGS, then you need to take that into account, and basically there's a transfer relationship that we calculated before between that current, input referred current and voltage. But let's just quickly calculate the input referred voltage source. So V in over delta F. Okay, so what do we have? Well, how do we do that? When in doubt, calculate the output noise and divide it by the transfer function's magnitude squared, right? From the input to the output. That's the general procedure. It always works. But sometimes you just can look at it and tell for some of these calculations, right? And you should be able to do that eventually for all the circuits. So how do we do that? Well, we know that these three sources are uncorrelated. They're generated by three different physical phenomena, or at least different physical phenomena at different places. And okay, so this one is already at the input. So we know it's going to be there anyway. So it's a superposition. And so since they're uncorrelated, you get the power spectral density of each one of them. So you get Vf squared, magnitude squared over delta F plus. Now, how does this noise current source at the output translate to a voltage source at the input? What is the transfer function from this a voltage here to a current there? GM, right? GM's magnitude, GM squared really, at low frequencies if you think about it. So you have to divide it by GM squared. So you get basically 1 over GM squared times whatever that channel noise is. So we can call it I channel divided by delta F, so which is this quantity. Plus, then how about the resistor? The same deal. It's the same current, right? Because it's a current between a ground, because this is AC ground, and this node. So again, goes through the same transfer function. You can actually, in fact, write it as I res R over delta F. So that's my input referred voltage noise. You can plug in values in there. So you can just basically, then you get KF Cox WLF plus this thing, which basically gets you 4 KT gamma GD0 over GM squared plus 4 KT over GM squared R. And yes, if it's a non-velocity saturated device, this will become only for non-velocity saturated device, non-velocity saturated, it becomes GM, so this becomes 1 over GM. And if it's a velocity saturated device, it is what it is. Okay, so this is the input referred noise of this device, input referred voltage noise of that. And if you do a current source, then it's related essentially through the impedance that you see here. So if you look at this impedance looking into here and call it Z pi, so if you want to look at the equivalent input, the current source in general, it would be basically the relationship, the same thing as the voltage except for the Z pi. So you basically have to divide this by Z pi of F magnitude squared times V in over delta F. which in this case would produce something that's 100% correlated, right? Because it's derived from the same sources. So this is what you get for your common source. And you can get it, you can add more noise sources and all those things, but just in that sense, interesting. And we'll do a numerical example shortly. But so that's basically what that is. Now, how about other stages? Let's start talking about, so we've talked about this a couple of times, so I'm not going to get too deeply. So how about common gate? Let's look at the common gate and see what the common gate does. So let's look at the common gate stage. We know how it looks like. It basically, so we are not showing the biasing detail, obviously. So you have a resistor R1, you have some V bias here, and then you will have an input that's applied here. And what are the noise sources? Let's even forget about the flicker noise for a second. And let's even look at the basic, the channel noise and the resistor thermal noise. So this is 4kT over R1, and this is 4kT gamma GD0. These are the current power spectrum. So what is the input referred voltage source? Input referred voltage noise source. It's basically the voltage source that produces, so a voltage source that you need to produce at the input or use here to generate that output, the noise at the output that we anticipate to get, right? Yeah. So what is that noise if you have a voltage source there? So let's look at the individual, use superposition, right, of the two purple ones. So each one of them is injecting a current 4kT gamma GD0 and 4kT R1 into that node with a resistance R1, right, to ground, AC ground. So the total output noise, V out over delta F, is going to be these two things. So it's going to be R1 squared, IR squared over delta F plus I channel squared over delta F, which are this and that. And then, so that's the output noise, the noise at the output, the power of the out noise at the output. Now, I want to reflect it to the input. Now, I have a different input this time from the previous example, so I have to calculate what is the voltage gain from here to there, right? What is the voltage gain of the common gate? Remember, right? It's just GM-R1. It's a non-inverting stage, right? Because really, you're changing the VGS. Here, you're changing the VGS by moving this one up and down. Here, you're changing the VGS from a small signal perspective by this and that. It's a little bit different. It's because that if you have a MOSFET, for example, you have to think about the body effect, right? So the gain really, you have, and in the case of MOSFET, you saw that actually both of these things are adding together. So the gain, AV, is basically GM plus GMB if you want to take that into account, R1. If you want to ignore the body effect, it would be just GM-R1. So that's the voltage gain. And therefore, the input referred voltage noise would be this divided by this magnitude squared. So it would be 1 over GM plus GMB, magnitude squared, R1 R1 squared times R1 squared, and those two terms in the parentheses, which is IR squared over delta F plus I channel squared over delta F. And these guys cancel, so what you're left with is essentially 1 over, let me just write it down here, 1 over GM plus GMB, magnitude squared, times the values of these things. So you can actually plug them in. You get 4kT over R1, and then you get 4kT gamma GD0. And you can see if GD0, if it was a non-velocity saturated device, it would be GM, so this would be close to 1, not exactly 1, and the other one is whatever it is. So again, depending on the relative size of GM, one of them can dominate. So that's the input referred voltage source, voltage noise, right? How about the input referred current noise? You need to calculate that too, right? So in that case, that's a current source sitting in parallel with the input, which basically would be like this. Now, in that case, let me ask you a question. What is the output noise? Is it the same or different? So the resistor part of the noise is the same, right? I mean, that's obviously the same because there is, so let's write that. So we are talking about, so this is again V out in this scenario. So this is V out magnitude square over delta F. So there's a current noise that's injection to this resistor, so you get basically 4kT R1. That's what you have, right? Now, what happens to this noise source? Does anything change for this noise source from the perspective of that noise source? What we've done is that we've changed that source, that orange source, that equivalent, from a voltage source to a current source, which means that we've changed the impedance in the source from 0 to infinity, right? So if you null that, what happens? It becomes open, not short. So if I have an open circuit here, think about this. It's an open circuit here. So this is open. Can any of this noise, for this noise to impact the output, this current has to end up in this resistor, right? I can redraw this slightly differently to maybe emphasize that point. It's a subtle difference in the way I'm drawing it, and this is the output, right? So for this to impact the output, this noise needs to somehow go into R1 to get converted to voltage, right? Would that noise go into the R1? Can it? No, because if you think about it, this is not connected really if this is open circuit from that perspective, from the low frequency perspective. This current is 0. Therefore, this current has to be 0. So all of this noise current actually circulates inside the transistor. It doesn't make it to that resistor to generate noise. So all there is at the output is really this. And if you want to reflect it to the input, you have to look at the transfer function from that output voltage to the input current. What is it? Well, what is the transfer function from the input current to the output voltage for a current source now? If I put the current source back, right? What is the transfer function from this current to that output? What is the trans resistance, right? It's the output ratio of output voltage to the input current. From a signal perspective, forget about noise, just from a signal perspective. What is it? What is the current gain of that transistor from the source to the drain? How much of the current in the source ends up in the drain? All of it, right? 1. So this current, whatever I in, shows up here and goes into R1 and produces a voltage. So what is the trans resistance? R1, right? So the ratio of, trans resistance, which is defined as V out over I in, is just R1. And therefore, if you want to reflect that to the input, then I in squared over delta F, so that the equivalent input current noise is going to be 1 over R1 magnitude squared times V out magnitude squared over delta F, which is going to be 4kT over R1, which should not be that surprising because this is the current at the output, right? That is the current noise at the output to begin with. And the current gain of this amplifier is 1. So it directly reflects to the input. It directly appears at the input. It's as if it's at the input. And a couple of observations. 1, first of all, the fact that whatever noise you have at your output, the current noise of the output, is directly appearing at your input because your current gain is 1, right? Is it a good thing or a bad thing? It's a bad thing, right? Because you don't get any reduction. So whatever you have at the output of this stage will appear at its input as current noise. So when you're dealing with a common gate stage, you have to worry about the current noise, usually, a lot of times, because that noise just directly appears at the input. There's no attenuation of that. You see, here there's an attenuation of the voltage by the gain, by this quantity, right? When it's referred to the input. There is no such attenuation for the current. And that's one of the weaknesses of the common gate amplifier stage. And it's still used. It still can be used even in low noise amplifier design, but you need to be aware of that. Right? So that's one observation. The other observation I have for you is that are these noise sources fully correlated, uncorrelated? What can you say about the correlation between the current, the input referred current source, and input referred voltage source? The two that we need to characterize any two-port noise system with two ports, right? Yes?
Correlated but not 100% correlated?
Say again?
Are they correlated but not 100%?
Well, so they're partially correlated, correct, exactly. They're not 100% correlated. Why? So which parts are correlated? Well, the parts that are produced by the same physical phenomenon, right? In this example, this is produced by the resistor, and this noise is produced by the resistor, the load resistor. So these parts are correlated. But there's this other part that's not present there and therefore is not correlated. So this is an example of a partially correlated two noise sources. So these parts add in amplitude, and this part adds to them in power. So you need to be thinking about how these things add. So that's an important example. And common source, so we are talking about our basic stages, so let's do the common source just for completeness. I'm sorry, not common source, source follower, common drain. So in a common drain, you have this stage, and then let's say you have some sort of a current source here. If that's all you have, then let's actually make the current source also a transistor. So it's something like that. Now again, we can take as many or as few noise sources as we want. Just let's take into account for now, for this thing, just two channel noise sources, right? So let's say you have this guy, and then you have this guy, these two channel noise sources. Let's call this M1 and M2. So this noise source is 4KT gamma GD, well, let's GD01, and this is 4KT gamma GD02. In general, the gammas may also be even different, but yeah. And then the question becomes, what is the gain of the stage? How do we deal with that? What is the gain of this amplifier? So let's say if this is RO, it's quite large. The output resistance is large. So you can think about from a AC perspective, you can think about it as being large. What is the gain of this thing if you take the body effect into account? Do you remember? It's a voltage divider between GM and GMB, right? Because you remember that if you think about the small signal model of the top transistor, kind of looks like that, right? So you have that, and then you have the parallel transistor. So this is RM, this is RMB, right? And this is a high impedance, so this is V out. And this is V in, and this is ground, right? So you have a resistive divider between RM and RMB. So the voltage gain is RM divided by RM, I'm sorry, it's RMB divided by RM plus RMB, right? The voltage across this guy. This is a resistive divider between V in and ground, and this is V out. And then, which you can also write as, if you want to write as GM, it becomes GM over GM plus GMB. And if you use that, then it's simple, right? I mean, so you can say this is the transfer function from the input to the output. You want to calculate what's the total noise at the output. Well, these two current sources are injected into the resistance that you see from here, which is dominated by the resistance you see looking up into the source of the M1, which is what? What is this resistance you see looking up here? I mean, you can see it from here, right? If you ground this, what is the resistance you see here? It's Rm parallel Rmb, which you can write as 1 over Gm plus GMB. Right? And then if you have that, so that's the resistance that you will see. So the total resistance, the noise at the output, V out over delta F, is going to be the sum of these two currents, the sum of the power of these two currents times the resistance you see over there, which is basically 1 over Gm plus GMB magnitude squared times the sum of those two. So you can actually, and you can factor that those common parameters for KT gamma, assuming they have the same gamma, be GD01 plus GD02. And if you want to take it into, and then what's the input referred one? You have to divide it by this gain magnitude squared, so which basically gives you, this magnitude squared gives you V in over delta F. So again, this divided by that cancels this term. You get a Gm squared. So you get 4 KT gamma over Gm1 squared, magnitude squared, GD01 plus GD02. And if they were non-velocity saturated, then this becomes Gm. So the input referred voltage source becomes 4 KT gamma 1 over Gm1 plus Gm2 over Gm1 magnitude squared. Gm1 is squared. So what does that tell you? That tells you that if you want to reduce the input referred noise of this thing, if it really matters to you, generally they're not as important in this case because they don't have that much gain, but still you need to worry about it. You don't usually put these at the first stage, and that's what matters the most. But yes, you need to get a higher transconductance here, but the transconductance of this guy actually is damaging, right? So you don't want the transconductance of M2 to be large. You want actually the transconductance of M2 to be small from a noise perspective, but you want the transconductance of M1 to be large and M2 not to be large, if that's the only thing you're trying to achieve, minimizing the input referred noise of this common source. Or sorry, source follower, sorry. One more quick example of this system in a scenario that you actually have a, let's say, active load. Let's say a situation where you'll have a common source, but now you have an active load. We've seen this scenario, and we see it frequently when you are designing high-gain amplifiers, right? So in one scenario, you can have an NMOS here and a PMOS there, which is some bias somehow. We know how to do these things. We've done a lot of those before. And then you have V in and V out. What is the gain of this thing? Well, if this is V in, then what comes out is GMV in. From a signal perspective, what is the resistance on the output? It's RON. And looking up, you see ROP, right? So it's a parallel combination of those things. So you know the voltage gain, AV, defined as V out over V in, is negative GM1 or GMN, and this should be GMN2, GMN RON parallel ROP. So these are some calculations we've done a lot before. So this is the gain, the voltage gain. Now how about the noise sources? Let's look at the noise sources. Let's do them in steps. First, let's look at the channel noise of the two transistors. And what is this one? This is 4 KT gamma N. Let's say they're non-velocity saturated. So we are assuming NV, non-velocity saturated. So this becomes GMN. And then this is 4 KT gamma P GM P, right? And if those are the noise sources, they are injected into something to produce the output voltage. We can always use the full procedure, which is converted to the output voltage. What is the output resistance here? How does this current convert to output voltage? Through the resistor RON parallel ROP, right? That's the total resistance on this node. So what happens is that it's this thing times RON parallel ROP plus this thing times RON parallel ROP. So we can do that. Let's write it that way. V out squared over delta F. And then you get 4KT. So let's say RON parallel ROP times 4KT gamma n GMN plus 4KT gamma p GMP. Okay? And then magnitude squared. And then the input referred voltage source, voltage noise, is this divided by this magnitude squared. So you get the RON parallel ROP cancels. You get 1 over GMN squared times 4KT gamma n GMN plus 4KT gamma p GMP. And then, of course, when you simplify it, you get 4KT times gamma n over GMN. One of them cancels. And then you get gamma p GMP over GMN magnitude, GMN squared. So this is your input referred voltage noise. What do you have? Well, again, what matters really is what are the parameters and how they affect the noise, right? That's not the takeaway. Otherwise, it's just a bunch of symbols and equations and things of that, so they're useless by themselves. So it says if you want to reduce the input referred noise, you need larger GM, right? For this kind of noise. This is white noise. This is like flat white noise, thermal noise. So larger GMN helps. Larger GMP doesn't help. The transconductance of NMOS does not, PMOS does not help. So actually it hurts. And why is it? I mean, can you explain that why increasing GMN helps and increasing GMP hurts?
If you increase GMN, you're also increasing your gain.
Your gain, right? GMN affects the gain, but GMP doesn't. And it helps because it's the input referred noise. So it gets scaled by you get more gain. Another way of saying it is that you get more signal at the output. Your signal becomes stronger. Because if you look at the output noise, increasing both GMN and GMP seems to have the same effect, right? So yes, you increase GMN, you get more noise at the output. It gets noisier. If you have a noise meter there, it looks worse. But a signal of the same magnitude coming in would appear larger at the output. So the signal to noise ratio would improve. So that's, again, to think about why these things affect it. So for example, if my input was here instead of here, if I had biased this here and the input was applied here, what would you imagine would be the parameter that would which GM would be helpful and which GM would be hurtful if we increased it? So now it's going to be the opposite, right? Because if the input is here, this is where my gain is coming from. So that if my input was applied here, then my GMP should be larger, because that would increase the gain from the input to the output, and GMN to be smaller. So what affects what is a function of where you chose your inputs and outputs and how you apply things. We saw this in case of transfer functions, things of that sort, and it also applies in noise. So that's important to think about. So that's the thermal noise. How about flicker noise? What if we had flicker noise or 1 over F noise? So what are the two sources of flicker noise? One is here, and one is here. So this one is, let's say, KF, whatever, KFP over Cox WP LP F, and this is KFN divided by Cox WN LN F. So these are the two input voltage sources, the voltage sources. So what is the input referred voltage source due to the flicker, or input referred flicker noise? So this was the white noise part of it. Then we have to also think about what is it that it appears at this input due to these things. Again, we can go the long way or the short way. Let's go the long way first, and then we'll do the short way shortly after. So the long way is to calculate the effect of these two things on the output. That's where the noise will appear, will show up. So I need to add terms to these things. And I need to really add them in power the way they are because they are uncorrelated. They are caused by different physical phenomena. So there will be additional terms here, right? So what is the transfer function from this voltage to this voltage? We kind of just talked about it. Right? What is the gain from this node to that node? It's GMP times RON ROP, right? Because it's the transconductance of this transistor is now amplifying. So what you see there is you see GMP RON parallel ROP times that flicker noise of, you can call it like just VFP squared over delta F. Okay? So that's the transfer function from this point to that point. Now, the transfer function from this voltage to that voltage is just basically the gain that we have already calculated, right? Because it's the same terminal. So that one would be amplified by GMN magnitude squared RON parallel ROP, and this should be squared too. VFN magnitude squared over delta F, so the power of that. So now these two new terms are due to flicker noise. Does it make sense? Yeah? So now I have these two additional terms. We have these two additional terms. Now we need to reflect them to the input of the amplifier. Right? How do we do that? We divide it by the gain magnitude squared. Right? So when we do that, well, this part is already there. So what happens first to this part? Well, you can see this is the gain itself, the gain squared. Right? So that would just disappear. So that, which makes sense, right? So you get VFN magnitude squared over delta F, which I can write simply as just what it is, KFN Cox WN LN F. Plus, now you get this guy divided by this gain magnitude squared. So RON parallel ROP part of it cancels, but you get a GMP over GMN. So you get a GMP over GMN squared KFP divided by Cox WN LN F. So what you can see is here is that, of course, these two terms are giving you 1 over F behavior. So if you look at the power spectral density of this noise, there are these guys that are give you 1 over F noise behavior, and there are these black ones that are give you flat noise behavior. So overall, you see a spectrum looks like that versus frequency. Right? So now the other thing that you see is that the flicker noise of this guy is just directly there, which kind of makes sense. I mean, you could have said that from the beginning, right? That's where the noise source is. We didn't really need to take it to the output and bring it back to the same place, right? Now, and this guy, being at a different place, it goes through the GMP of this guy and then gets divided by GMN of this guy. And that's why you get the ratio. So if you're trying to minimize the noise at the input referred noise, again, as far as GM is concerned, the same trade-off applies to both components of the noise, right? Increasing the GM will reduce the input referred noise, GMN. GMP doesn't help, actually it hurts. And we can see that. But now we can also translate it even to device parameters, right? We can say, what are the device parameters? There's no, when you make a transistor, there's no parameter GM that you pick, right? You pick, what do you pick when you design? You pick W and L and things of that sort, right? The width and length. Let's talk about this, and the current, operation currents and things like that. So let's think about that. What would W do? So let's say if you increase the width of the NMOS here, what would it help and what would it hurt? Let's think about it. So increasing the W and everything else being the same, assuming everything else remains the same, what happens to GM? GM goes up, right? So GMN goes up, which basically means that the input referred noise would go down, right? Would go down. What else happens? How about the flicker noise part? Well, the flicker noise part, oh, this should be P. These are P's. Okay. WP, LP, okay. The flicker noise part, this component of the flicker noise also goes down, right? So the 1 over F noise also goes down. 1 over F noise of N goes down. 1 over F noise of P also, if its effect goes down because GM is going up, right? So both of so that helps. So it sounds like a pretty good thing to do, right? What is it that we are losing when we do that?
Speed.
Speed, exactly. Why we are losing speed? Capacitance, right? So the capacitance is also going up. So this means that C is going up, which means that the omega F3 dB or something like that, the bandwidth, or let's call it bandwidth, is going down. So there's a trade-off there between speed and noise as well, right? Now, how about the current? What if we scale the current? Let's say if we take the I bias, ID, and increase it. What would happen? Well, GM goes up, which would again help with the noise stuff. But what is the price? It's even a more obvious price, right? It's power consumption, right? So the power consumption is going up too. So there's also a trade-off between noise and power. So there's a trade-off between noise performance and speed. There's a trade-off between noise performance and power. And there's a trade-off between power and speed, as we've discussed before. So depending on where you want to be in the design space, you may choose different parameters to achieve the design objective that you have. Okay. Let's talk about a couple of quick examples. So just like let's talk about a couple other things, and then we'll do one numerical example. So if you're good with this, let me erase some of these calculations and go to a different discussion. Okay, so how about we talked about our 3 basic stages, right? The common emitter, common source, common drain, common gate, right? Now, how about a cascade? These are the stages we see frequently, right? What happens in a cascade? Now, we will try to kind of like start talking about noise and try to transfer the noise from one source from one location to another a little bit more implicitly as opposed to explicitly always taking it to the output and bringing it back to the input. The same way that, you remember when we started with talking about gains, initially we drew the small signal model every time, but eventually we learned how to do it in our heads. So we can do a similar thing with noise sources. And we need to learn how to do that so we can actually gain some intuition about how to deal with those as we go. But, okay, so let's look at this stage and see what happens to various noise sources in it. And we have essentially the core ingredients of this discussion. I just want to make sure that we talk about them a little bit more explicitly. So what are the noise sources we take into account? Let's just think about the channel noise of this guy, the channel noise of M2 and M1 and M2. Let's call this M1 and M2. And then the thermal noise of R1, right? So this is 4 kT over R1. This is 4 kT gamma G M2, let's say they're non-velocity saturated, 4 kT gamma GM1. But if they were velocity saturated, then this has to be GD0. If they're non-velocity saturated, GD0 is equal to GM. I'm repeating this thing because it's important. It's not always GM. It's only if they are non-velocity saturated. But anyway, so we have these 3 sources, and we want to find out what is the input preferred noise. Let's see if we can talk about them one at a time and see how they behave. So this noise source, the current noise source of the resistor noise, right? This would translate to a voltage directly here through R1. Let's say RO is much larger than R1, so we don't have to worry about that stuff. So it's basically this times R1 that produces the output voltage. Now, the transfer function from the output voltage to the input is a known thing, right? It's a gain, which is negative GM1 R1, right? The low frequency gain is that. So I know that whatever voltage I have here, I can put a voltage source here of that voltage or voltage divided by this magnitude, or that voltage power divided by this magnitude squared. Right? So I know that at the input, due to this resistor, I will have 1 over GM1 squared R1 squared times this times that, which would produce the voltage for KT R1. So that's basically the contribution of this thing at the input. I'm reflecting them to the input, right? And we are doing the same thing, but just in one shot as opposed to 2 steps to get used to that. Now, how about this guy? Right? Whatever you see here, you could put a voltage source here and then say this voltage gets multiplied by GM of this thing to produce this current, right? So to reflect this to the input from here to there, I have to divide it by GM1 squared. So I get plus 1 over GM1 squared times 4 KT gamma GM1. So one of them cancel, you're left with that. So that's the contribution of those two, which are more straightforward. The question is, what is the contribution of this guy to the input? Let me ask you another question. Well, to understand what the contribution of that thing to the input is, you have to understand what its contribution to the output is, right? The output is the key to understanding what happens really to the noise. So what is its contribution? Well, think about it. How is this current divided here? Now let's look at the small signal model for this guy. If you look at the small signal model for that, and just forget about the body effect or something like that. So this is R1. This is IS2. This is IS2, right? This is ground. It's the gate V bias. And then you have the RO1. And this is where that noise source is sitting. Okay. That current source is, you can see that both of these ends are grounded, right? So there's a current divider between these two resistors. This is RM2 and this is RO1. Where would most of the current go? RM2, exactly, right? Because it's much smaller than RO1. So most of your current is really circulating here. So, and as such, since this current is really small, this current is also really small due to that. I mean, how small? Well, it's determined by the ratio of RM and RO. It's usually a small ratio. If you want to do it exactly, the current that goes into this guy is RO, the current that actually goes here, that's what matters, right? Is RM2 divided by RO1 plus RM2, which is roughly RM2 over RO1. So that's the ratio of the division of this current. This is the fraction of this current that ends up at the output, which is a very small fraction. Right? So you can see that it doesn't contribute a lot, at least in this current setting, the way we've set it. So you could, for the most part, ignore it. If you don't want to ignore it, you just basically take whatever that current is and multiply by this ratio to get it to the output and then reflect it back to the input through this gain. But really, it's not a major player because it circulates there, because it sees a high source impedance. So whenever you have a high source impedance, so this is kind of something a little bit more general. Whenever you have a high source impedance, which is the case here, right? This noise source will mostly be confined internally because of this effect. So you need to think about that. That's fine. But now, what happens as the frequency increases? As the frequency increases, well, we haven't taken any capacitors or anything into account, but there could be some capacitance here. So if there is a capacitance here, then it's really, let's say, CO1. Then the division happens between, let's say, RM2 and ZO1, right? And as Z01 becomes smaller with frequency, this division ratio becomes smaller. So basically, if more and more of the current can flow in this direction, which basically means that, just connect it in the place that's easier to see, which means that this current is not going to be 0 anymore. And then it starts contributing to the system. And you can calculate how much by just calculating this ratio. So that's one other thing. The other thing to think about, another stage to think about, is what we call the differential pair, right? It's a very common kind of stage that we have. So let's think about the differential pair. Let's think about the noise behavior of a differential pair and see what happens. And let's keep it relatively simple for now. Let's just only think about the channel noise of the two transistors. You can use MOSFETs, you can use bipolar, it doesn't matter. So let's do the example with the MOSFET. So you have a channel noise here, and you have a channel noise here. So what can you say about these two noise sources? Are they correlated or uncorrelated? They're uncorrelated, right? The two different transistors producing noise separately, so the electrons in one don't know what the electrons in the other ones are doing. So in that sense, what can you do in terms of finding the transfer function for each one of them? What we're trying to see is what's the equivalent input referred voltage noise, for example, right? What noise source I should put at the differential input of this thing. So the question is, what is the transfer function from this current to the differential output? You can use superposition, though, right? Because they are uncorrelated, so you can actually calculate the power effect of the power of each one of them. So let's say this noise source was not there. If you had one noise source here, what would get to the output? So think about it. What fraction of the noise gets to the output? Well, you were trying to calculate the transfer function from a current here to the output, right? There are different ways to think about it. One way to think about it is that, well, from a small signal perspective, what do you have? So if you think about it from a small signal perspective, this is what you have. You have Rm here, and then you have Rm here, right? If this is grounded, and this is grounded in this case too, so there is a current source here, and then you have R1 and R1. And this is your differential output. So if I put a noise source here, here actually, how would it divide between the two RMs? Evenly, right? So what happens is that half of this current goes here, and half of it goes there, right? And this half that goes there, it reflects up here. So what is left is the other half, right? Because this half is the same half. This current source is reflected. So what is left is the other half. So the other half goes into the R. The other half, so let's call this like the component I1 and I2. We know they have the same power, but they're not necessarily the same. So the part that goes into, but they're correlated, right? So they are correlated. They are coming from the same source. So it's basically, you can call it, well, basically call it I1 divided by 2 and I1 divided by 2. So half of it goes through here, which goes through here, and then basically what you have is the other half. So you get I1 over 2. Because I1 over 2 is going through here. This is I1, if this is I1. And then I1 is going through here, and now I1 is also injected this way and appears where? So it goes up. So this is going to go into this guy. So you have the effect of this noise on the output like a differential signal, right? And what happens is that so you have a transfer function from here to the output and you have a transfer function from there to the output. Each one of these transfer functions can be calculated independently, and you have two of them. So what this stage does, it produces, you have two noise sources now instead of one. But what is the gain of this stage? Think about the gain of this stage, right? What is the gain of the stage? If each one of them has a GM, the differential gain. So let's say each one of them has a transconductance GM. GMR1, right? So you have a GMR1 is the total gain from this differential input to this differential output, but which is the same as the gain of a single common source. But you have now two noise sources. Each one of the noise sources that you had one of, now you have two of, right? Because you have these two that are uncorrelated. And if you look at the noise sources of these two, they are going to be uncorrelated too, right? So for the same gain, you have twice as much noise. So from that perspective, it's not necessarily better from the intrinsic noise, because you have twice as many noise sources to produce the same gain. So that's why if you're really, really interested in pure intrinsic noise reduction, so noise people refer to noise differently, right? We talk about interference, which is what comes from outside to the circuit. Let's say somebody else is running some digital circuit next to you, or some motor is running and all those things and stuff that couple. You're not talking about those. That's called interference. That's something that's not intrinsic. You can get rid of, in principle. You can shield things, you can cover things, you can produce less noise, et cetera, et cetera. And differential pair is great for that stuff, right? Because it has differential to come. There's basically the common mode rejection. You can make that common mode. That was one of the primary points of using differential pair for interference reduction. But let's say you've gotten rid of all of that. You've gone to Antarctica and in a very quiet area, and there's nobody kind of like generating anything else. There's no Wi-Fi. There's nothing else around. You can like to generate all sorts of kind of noise, and there are no TV station, radio stations, cell phone towers, things of that sort, motors, nothing. And you put this in a perfect Faraday cage. You've shielded everything. You don't see any interference. If you're intrinsically limited by noise, though, this stage is not only not advantageous, it actually has a disadvantage, because it generates more noise for the same amount of gain. And those kind of amplifiers you see a lot of times, they're actually done as single-ended, or things that are done for radio astronomy or cryogenics and things like that. So a lot of times you will see them. You don't see a lot of differential design there for this, because of this effect. Okay? So that's for a differential. Now, let's do a quick numerical example, which I think is helpful to see another concept that's important. So we've done everything parametrically so far. Let's do something numerical. So let's take this, erase that. And let's say you have an amplifier. Let's say you have a basic common source amplifier with some load resistance. Let's say your transistor does have some source, there's some gate resistance, either intrinsic to the transistor or is coming from something else that's there. So you have an RG, you have an RD, and then let's say you have a VN. Let's say you have a supply voltage of whatever, supply voltage of whatever, 5 volts. You have a V-in, let's say, DC voltage of 1.5 volts. Let's say RG is 10 kilo ohms. And let's say RD is 1.5 kilo ohms. And then the transistor parameters, I'm assuming Tox of 40 nanometers. It's a pretty big transistor. And that would give you mu and Cox of, so that would give you a Cox of 8.6 10 to the minus 8 farads per meter squared. And then you get mu and Cox of 60 microamps per volt squared. Let's say the threshold voltage is 0.7 volts, and the coefficient of the flicker noise, Kf, is 10 to the minus 24 volt farad squared. Oh, no, volt squared farad, sorry. Volt squared farad. And let's say the noise gamma is 2/3. So if you take these parameters, you can calculate, first of all, what the DC current is. ID is, let's say it's non-velocity saturated, so mu n Cox over 2, W over L. Oh, I have to say what W over L is. Let's say 300 micrometers over 3 micrometers. So it's a pretty long channel. You can really, it's not going to be velocity saturated for the 5-volt supply. Okay, so this basically becomes mu n Cox over 2 W over L VGS minus VT squared. So this is basically the quadratic behavior. And if you plug in the numbers, so you have 30 microamps per volt squared times 100, which is the W over L, times 1.5 minus 0.7, so it's 0.8 volts squared. And that would translate to a current of 1.9 milliamps. Okay, I mean, these are some numbers, right? I mean, and that would correspond to a GM. You can calculate the GM, which is mu n Cox W over L VGS minus VT, which is the GD0 as well. So the GD0 is not being a non-velocity saturation, it's equal to that. It's 4.8 millisiemens. Okay, so these are the parameters. Okay, so now what we need to do, we need to look at the noise sources. Let's look at the noise sources first. What noise sources do we want to consider? So what noise sources should we consider? There is the flicker noise of the transistor, which is sitting here, right? There is the channel thermal noise, right? I channel squared over delta F. There is a noise of the output resistor, I d squared over delta F. And then there's the thermal noise of this gate resistor, right? Which is Vg squared over delta F. So this is obviously 4kT Rg, and this is 4kT over Rd. So let's see how do they reflect to the input. Let's look at the input referred noise. There are 4 noise sources you're taking into account. 3 of them are white noise sources, right? They're flat. They resist the thermal noise of this guy, the thermal noise of the channel, and the thermal noise of the drain resistor. And one of them is 1 over F. So let's start with what we get from the input referred, the output noise and the input noise. Let's calculate the output noise and input noise. Now, if you think about these, the output referred the input referred noise, so these 2 are already at the input, right? We can take them to the output and bring them back, but we go through the same transfer function, so we might as well keep them there. Right? We know that's going to be at the input. So let's write that down. So V in squared over delta F is going to be, you can write even, we can write it explicitly. We can say Vf squared over delta F plus Vg squared over delta F plus, now you have these 2 noise sources that are injecting current into the output node. What's the resistance on the output node? R1 or Rd, yeah, in this case it's Rd. And what that is basically going to be divided by, so they're going to inject into this to produce a voltage Rd, and then you're going to need to divide it by Gm Rd, right? So you divide it by 1 over Gm squared, because Rds will cancel. 1 over Gm squared of times you have Id squared over delta F plus I channel squared over delta F. So if you explicitly express these things, these 3, of course, so now let's expand it. Kf over Cox WLF plus 4kT times Rg from this term. Then from this, the resistor noise is, so that's basically 4kT over Rd. So that becomes Gm squared Rd. And then you have this guy, which basically has the 4kT. So you have gamma over, and then you have Gm. So basically you get gamma over Gm if it's non-velocity saturated, right? So those are the 3 sources that you will see. Now, if you look at the spectrum of this input-referred noise, what do you see based on this calculation? The spectrum of the input-referred noise is going to have a 1 over f region and then a flat region, or a white region. So in aggregate, you are seeing you're seeing something that will look like that, if this is log of f, really. So this is the power of the input-referred noise. It looks like that. Now, this part is contributed by the flicker noise. You can put parameters in there and calculate what it is. We can do that. And then we can calculate these parameters and see which one dominates. Let's just do a quick calculation, right? Because we know the parameters, the numbers. So let's see. If we have these three things, if RG, we said, what was RG? We said it's pretty large, right? 10 kilo ohms. Now, what is this quantity? GMRD, the gain, 4.8 times 1.5 kilo ohms, right? So it's 4.8 times 1.5, so that's 7.2, right? So it's a gain of 7.2, and 1 over GM. So it's 4.8. If it were 5, RM would be what? RM would be 200 ohms. So this is a little bit, let's say 200 ohms divided by 7, right? It's like 30 ohms. And then this one is 1 over, so we said it's 200 ohms, so times 2/3, so it's like, let's say, I don't know, 150 ohms. So what is the major contributor here to the total noise? I mean, we can multiply by 4 kT. But that tells you which one, what is the major source of noise at the input right now? The gate resistor, right? Because this guy is 10 kilo ohms, right? And these are on the order of 30 ohms and 150 ohms. So the gate resistance is dominating your noise, the white noise, by far, if you pick this value. It's 10 kilo. Even if you were at 1 kilo ohm, you have to be around 100 ohm for it to be comparable. Right? So if you pick these, if you keep these values, you'll be dominated by that. Your noise floor here would be dominated by that. The flicker noise, no. The flicker noise is dependent on the W and L, and you can pick up some values and calculate them. So that's one thing, but that assumes that there is no frequency response, right? So let's just, to see something, to get a feel for something, let's just assume that you have just one capacitor. Let's add one capacitor to the circuit. I mean, we can do more, but we want to see what happens. So let's say you have a gate capacitance here, CGS, or CG, whatever, Cin. Let's call it Cin. What if we have this one capacitor? What would happen to this noise calculation? Well, what would change when you have this capacitor? The transfer function will change, right? Now, these two noise sources, this one is before that capacitance, so this is already at the input anyway, right? And this one, you could argue, yeah, well, this is inside the transistor, et cetera, et cetera. It doesn't matter because it's low frequency anyway. That's not the frequency at which the capacitor is. So these two are not going to be affected by it. But what would happen is that what you get divided by changes, because now it's not just GM_R1 anymore. What is the new gain? So we have to calculate what the gain is as a function of frequency. So A of S is going to be GM_RD divided by 1. So now, what is that? How many poles would we have with one capacitor? Obviously, one pole. Are we going to have a 0 where we put the capacitor? No, because shorting it would result in a 0 output, right? So we know we have one pole. What is the pole frequency, or what's the pole time constant? What's the resistance seen by that? RG. So it's going to be basically RGCNS. So what we are interested in is really the magnitude of A of F, right? Magnitude squared, which is going to be, well, I think there's a negative sign here, minus sign here too, but that doesn't matter anyway. So it would be get GM squared RD squared divided by 1 plus 2 pi RGCNF magnitude squared. So this is the transfer function magnitude squared due to that one capacitor, if that was the only capacitor there. So now these output noise sources that you had, they get multiplied by RD to produce the output. They get divided by this transfer function. Right? Before, you had divided only by the top part of the transfer function, GMRD, and the RDs cancel, and you were left with GMs. So what would change here is that now instead of this, you will get a different expression. Let's say, so now these two terms will change. So now the Vin, the new Vin squared over delta F, would have the two input parts of the noise. Let's just write them in those, keep them in those forms for now. But now these guys, you still have the GM squared, but now you have to divide by that. So when you divide by that, this denominator will appear in the numerator, right? When it's referred to the input. So what you will get is that you will get 1 plus 2 pi Rg Cin F magnitude squared divided by Gm squared times those two. You agree? What does that mean? How does this look? I mean, you can explicitly write these things, right? So this part, this is the flicker noise. This is the 1 over F noise. So this is still there in the power spectrum. This part is the noise of the input resistance. Now, whatever value, that value obviously was clearly crazy, right? Too high. But if you even just change that from 10 kilo ohm to 100 ohms, still would produce something, right? Some value. But it doesn't matter. Just like, so whatever that is. But that's white noise. That's not affected by this transfer function, because that was already at the input. So that part contributes. So if you look at now the output, so let's look at the output and input. Let's say this is the input, preferred noise. So this is V in squared over delta F versus frequency. And then this is V out squared over delta F versus frequency. So what happens? You have the flicker noise part, and then you have the RG part, and then you have these two guys. So from the output perspective, these two are there. There's right now we haven't introduced any capacitor there, so those two will stay up there, right? So they are there, but the contribution from RG, what happens to it? Once you hit this frequency, right, it starts dropping, because that's going through this transfer function. The noise due to RG is going to get attenuated at the input. So it doesn't get as much to the output, so you basically just drop here. So you go from the sum of the three noise sources to only RD and channel. So your overall noise response will look like that at the output. This is what you will measure. This is something you can measure. But from the input referred noise source, look at this. What happens? Well, this part is that part. That part is not changing. This part is the contribution of the resistance, the gate resistance, plus before this kicks in, at low frequency, if the frequency is below this frequency, right, you will get the same expression as before. So this has all three contributions. So this is all three of them, as before. So this is like before. But now, when you hit that frequency, let's say, I don't know, F in, what would happen to the input referred noise? It increases. So the input referred noise of this circuit will look like, because now you have an increase, and it's a square dependence on frequency. So it's steeper than that. This is 1 over F, remember. But this is 1 over F squared. So overall, your noise behavior will look like this. So this is 1 over F, and this is F squared over the frequency. So the input referred noise behaves like this. And the reason this goes up, why does the input referred noise increase at high frequencies? intuitively?
The gain drops.
The gain is dropping, exactly, right? So you're getting less gain, so it appears like you have more noise at the input. You need to put a larger noise source at the input to get the same noise at the output, although the noise at the output is actually going down. So, but now, a lot of times when you look at amplifiers, when you characterization, if you look at the data sheet of a transistor, if it's low noise, you will see plots like this. Again, this increase that you will see at high frequencies is a fictitious increase. It's not there. You cannot go and measure that, but it's a relevant one. Because if you had a signal of a certain value, it would result in a lot smaller signal-to-noise ratio at high frequencies compared to low frequencies. So that's what that means. Okay? All right. So all of these things, actually, this input-referred noise business leads to something relatively intuitive. That if you think about the kind of like the takeaway from, if you don't want to get into the nitty-gritty of the noise calculations and parameters and things like that, so which you should at some point, but if at sometimes you don't want to kind of think about it too much like that. You may want to say, okay, from a simplistic perspective, what is the thing that matters? So imagine a simple scenario. We are going to make a simplified scenario where you only worry about, let's say, a voltage source. So let's say you have an amplifier, and the impedances are such that you're dealing with high impedances, et cetera, that the amplifiers can be modeled with just a voltage source. Let's say Vn1, A1, and then you have a cascade of amplifiers. So you have a second amplifier, Vn2, A2, and so on and so forth. If you have a scenario like this, well, let's do one more. Just Vn3, A3, and then keep going. So if you have something like this, and this is a very simplified version, and then you can generalize it to the case where you have both the current and voltages, but the takeaway is the same. What is the total input referred noise if you have something like this? If the impedances were high, so you don't have to worry about the current sources, the input impedances were high, the output impedances were low. Let's say the output impedances of these stages were 0, and the input impedances were infinity. So they're like ideal voltage amplifiers. So you don't have to worry about the current for now, just to make it simple. Now, what is the input referred noise, total input referred noise? So each one of these amplifiers may have a whole bunch of noise sources, but we've lumped all of that into one source. But you have a cascade of amplifiers. So what is the input referred noise? Well, let's say you have n stages, Vn, well, Vnn, An, right? What is the total output noise, if you're in doubt, right? So the output noise due to this gate, so V out squared over delta F, is going to be this noise, right? The power of this noise source times all of the gains squared, right? So it would be Vn1 squared over delta F times A1, A2, all of them squared, multiplied to An. This one, the second one, goes through all of them except for A1. So you start with A2, A3, all the way to An. And so on and so forth. So the last one, Vnn, would only observe what? The gain of the last stage. So that's the total output noise. But now what is the input referred noise? So to calculate the input referred noise, you have to divide it by the total gain, right? Is 1 over A1 squared, A2 squared, all the way to An squared times the output noise power. And if you do that, you can clearly see what you see is Vn1 squared over delta F. All of these cancel in this term. 1 over A1 squared Vn squared over delta F plus 1 over A1 squared, A2 squared, Vn3 squared over delta F, all the way up to 1 over A1, A2, to AN minus 1 squared, VNN squared. So what does this expression tell you? This is, by the way, called Friis equation. There are two Friis equations, one here and one in antennas. So they have nothing to do with each other. There are two of them in electrical engineering. But so this Friis equation. What does that tell you? What does this equation has an important lesson. What is the most important noise source in this chain? The input one, the first one, right? Because that has the most contribution to your input noise. And then the effect of the noise of the second stage is attenuated by the gain, well, more accurately, by the power gain of the first stage, or the voltage gain squared in this case. And the effect of the third stage gain is reduced by the gains of the first and second stage. So if you're making a sensitive receiver, where noise is important, for example, if you're making a transimpedance amplifier for an optical receiver, right, that has a high sensitivity, requires a high sensitivity, where is the place where your noise is dominated? What is the place that you have to pay the most attention to the noise? Your first stage. That's why receiver chains start with an LNA, low noise amplifier, and then do other things, right? And people rarely talk about the noise performance of the last stage. If you already have a bunch of gain, it's not going to matter as much, because its noise is going to get attenuated by the gains of the previous stages. So it's the noise at the input that matters the most, and how much it matters is basically a question of how much gain you have prior to that, preceding it. So this is an important observation, that when you make low noise systems, the first stages matter. Now, an interesting other subsequent conversation, we haven't talked about this yet, but it's in terms of nonlinearity, right? What if you have a chain of amplifiers and in terms of nonlinearity? The nonlinearity is opposite, because your signal is weakest here and gets larger and larger. So the nonlinearity of your last stage is the most important one in a chain. That's, for example, when you're transmitting, it's the nonlinearity of the power amplifier that people talk a lot about, because that's a transmission chain. Or even if you're receiving, the nonlinearity of the last stage matters, because that's where your signal is the largest. So nonlinearity goes in the other direction, actually, in significance. And noise goes in this direction. So that's one way to think. So this is kind of like gives you a very basic foundation for dealing with noise and understanding how it progresses and it's processed in a circuit as you deal with various kinds of transistors. We saw that there are various kinds of sources, and then we can see that we can abstract them away into these like input-referred noise sources. In general, there will be a current source and a voltage source, and all of that can be reflected again to the input as a pair of noise sources, and we'll see that the input basically has input amplifiers play the most significant role in the noise performance of a system. Okay? Any questions?